Hello, everybody. I hope you're doing well. So this week we're going to focus on problem set number 7, which deals with SVM. So up until now in class, for classification, you've seen linear regression, which is a clumsy way of doing classification. And then you saw a more appropriate method, which is logistic regression. Here we're going to focus on a new method, the new method which you've seen, which is support vector machine, or SVM, which is for classification. So you've seen in class that the problem we want to minimize is given in 1 here. And you can recognize that it's the same as for logistic regression, except the loss we consider isn't the logistic loss, but it is the hinge loss. Then the question is, what's the best way to optimize this problem? So in the lab, you have access to a training set and a test set with features X and labels Y. So with this formulation and this hinge loss, you need to be careful that the Y's need to be in plus minus 1 and not 0, 1. So a natural approach to solve problem 1 is to use SDD. You could also use subgradient descent, but when big N is big, or large, then SDD is often more efficient than plain GD. So you have several functions to implement. One is calculate accuracy, which is just for a parameter W to calculate the accuracy on the train, excuse me, and the test data sets, as well as calculate primal objective, which is the loss function on the test and train set, and you need to take a parameter lambda into account here. I'd like to point out that for the accuracy, that lambda does not appear for the accuracy function. And then for question 2, you need to implement 2 SDD functions. One is just for a given data example small n, it gives back a stochastic gradient. And then there's the SDD for SVM demo, which performs SDD on the objective one. Okay, but you see in class that doing SDD on the primal problem isn't the best, isn't always the best way of doing. And you've seen that another approach is to consider the dual problem, which is given in equation 2. And this is a maximization problem over alpha. It's a quadratic function over alpha, which is concave, and so which is nice to maximize. It's constrained because you need the coordinates of alpha to be in the box 0, 1. And a way of solving this problem is to use coordinate descent or coordinate ascent in our case. And the first question is theoretical, and it's to show that you can have a closed form solution when you just focus on one coordinate. So you pick a coordinate n, and you want to show that there's a closed form solution to the maximization problem. And so what does this mean? This means that, so I pick a n randomly, and then I focus. So imagine I call my function of alpha here. So this is a function of alpha, and I call it f alpha. Then I pick a coordinate n, and I want to find the maximum, well, argmax of elf. So this is a vector. En is the vector which is full of zeros except 1 at coordinate n. And you need to show that this, so this problem, which is a 1D problem because gamma is an R, and don't forget it's constrained, this problem has a closed form solution. So you can write the solution of this problem. And then you need to update alpha, which is just the old alpha plus gamma star, which is the problem of this 1D problem, 1D optimization problem, plus en, which is the nth vector of the canonic base. Okay, so once you've answered this theoretical question, the implementation is quite straightforward, and you need to calculate the coordinate update, which is just to implement the this update. Then you need to calculate the dual objective, which is same as for the primal objective, but for the dual, so for equation 2. So you just implement this formula. And then you show the performance of coordinate ascent and with the function SDD for SVM And then the question is to see which one is is SDD faster or is coordinate ascent faster, and comparing the objective values of one in the two cases. Okay, and then the third part is a pretty theoretical part. So, okay, so you've seen in class that there are some kernels which you can write in a nice inner product form. But so here in the exercise, we call this a valid kernel. But in practice, it's often hard when you have a kernel key x prime. It can be quite hard to express it as an inner product. Actually, the feature map can be infinite. However, we're going to show here in these two questions that there are some operations which preserve the validity of kernels. So in class, I think you've seen that the sum of two valid kernels is a valid kernel. And if you multiply a valid kernel by a positive scalar, then it's still a valid kernel. And here we're going to show that if you have a valid kernel K1, and f is a polynomial with positive coefficients, so the fact that it's positive coefficients is very important. So if you compose the K1, which you know is a valid kernel by a function f, which is polynomial with positive coefficients, you need to show that this is still K, this is still a valid kernel. So this is nice because in practice, if you have a kernel K1 which you know is valid, then you know that K1 squared is going to be valid, which without even having to compute the feature map phi associated. And then 2 is to show that the exponential of a kernel is still a valid kernel. And so the hint they give you is that you're allowed to take limits, and I'm just going to explicit what this means. So what does this mean? This means that if you have a sequence of valid kernels, which is infinite, if Kn is a sequence of valid kernels, and if there exists a limiting kernel, which means that it's a pointwise limits for all x prime. So for all points x and x prime, you want your sequence to converge to some limiting kernel, which we call x, when n goes to infinity. So this is just a sequence of real numbers. And this is a real number. So this is a sequence which can converge. So the hint is that there's a result that says then K is valid. Okay. So this is a theorem which is given to you and which you can use to show question number 2. Okay, so that's it for this week. Good luck and have fun.